Hello everybody, in this video we are going to expand the model that we built in the previous module based on the instruction in the exercise document. First, let's rename the files so we know that they belong to module 2, and then we can open them, the script file and run it to check everything works fine before changing anything. So we can see that the script runs and the variables are available in workspace, but snum is displayed on the command window. We can avoid it by adding a semicolon at the end of the correspondent command line. And now we can see that it is fixed. Now let's open the Simulink file also and run it. It should run properly. Yes, it is. But what if we clear the variables from workspace by this command, clear all? As you might also expect, we will face an error that the variables are not recognized. So it means whenever we want to run the Simulink model, we need to run a script first. One solution to avoid this is that we can run the script from Simulink actually by adding a command line or by running the parameter file from Simulink in the callback initial functions of Simulink. Now, even so, the parameters are cleared from workspace. Uh, the Simulink will be run without facing an error because the initially the script will be run before performing the simulation. Now we can see also that the parameters are available in workspace because the script was run when running the simulation. Now let's expand the model actually, and this uref to the converter should come from a controller. Then we add a subsystem and name it PQ controller. This will provide the references for converter. Based on the exercise document, we can see there are three subsystems inside this PQ controller. One is ABC to DQ transformation. The other one is the controller, which controls the signals and the power and current. And the last one, the output of this controller goes to a DQ to ABC block to produce the references for the converter. Now let's resize them and yes, and make the connection between them. Always you can read this warning. Some of them give you some hint to do the things in simulation in a better or in a more efficient way. Now we can rename the input ports are also output ports. One of the inputs to the controller is the measured voltage and also the measured current we will have. I measured. Then also we can go inside the ABC to the each subsystem actually and name their input and output ports. For ABC to DQ block, we want to transform the voltage and currents from phase domain, ABC phase domain, to DQ domain. So the outputs will be UDQ and also IDQ. Probably it's better to call them to the inputs also with ABC, so we know that they are three-phase signals. We can do the uh, we can do the same for other blocks, the controller and DQ ABC, by renaming their input and outputs. The input to DQ to ABC is the voltage, and output is the three-phase voltage, which goes to the converter. Also for the controller, in the controller, based on the pictures in the document of exercise, we can see what are the input and output and insert inputs or duplicate or copy and paste the other inputs to make new input ports. So for the input we have PQ ref, PQ measured, UDQ and IDQ measured one. The output of this controller will be UDQ, which goes to the DQ to ABC block. Now let's connect the ABC to DQ block to the controller, and also we need to introduce new inputs, which are the PQ reference, which is the reference of the wind turbine, and also PQ measurement, which is the measured power at the terminal of the wind turbine. We can also make this subsystem as a mask. Let's don't change anything. Just it's good to make this icon transparency as a opaque with ports. So we make sure that even if we add a picture to this mask, the ports will be visible always. So let's do it for other subsystems also. Yes. Here is the main PQ controller. The output should be connected to the converter, and we can make the mask similar to previous ones here also. So let's change the transparency of the icon, and yes. Also, we can change the order of the ports on each mask by changing the numbers inside the mask. Here we have, I prefer to have P at the top and U and I at the end. Now we need to give the input to this controller. Since we are going to control the voltage, the power at the terminal at the filter bus of the wind turbine, so we are using the voltage and current at this bus to measure the P and Q at this bus and give the measured PQ to the controller. For the reference value, it should be an input because it is an input to the wind turbine, and we will the wind turbine or our model will receive it from an external signal. Yeah, we can always do the rearranging of the blocks just for a bit a good visualization of our model. Also, we can do the formatting. I I always like to I do the orange for the input ports and green for the output ports, but it doesn't matter. This formatting doesn't change the performance, and you can make it based on your preferences. Also, we always can press a space to fit the model to the window. That's how I fitted the previous blocks to the window. Let's start by building up these subsystems, and we start by DQ to ABC transformation. I started from this one because we always can test it step by step. So for this ABC to DQ to ABC, the input is actually DQ 0. So I am adding a ground and combine it with the input UDQ to make it UDQ 0, not to have an error of compatibility, to have the same dimension of the signals. Also, we need the omega t. So I inserted the input port to receive it from external. If we go inside the ABC to DQ the block and insert the ABC to DQ, we can see that we need the omega t also in this block. So since we are using measured voltage as a reference for the angle, we can obtain this angle of this voltage by a PLL and do the settings proper the sampling time and also frequency. Now we can see there are two outputs of this PLL. One is omega t that we are using. The other one is frequency that we are not using at the moment, so we can terminate it. Now by using this go to and from blocks, we can send this omega t to yes, we can send this omega t to DQ to ABC block. Always you can see, for example, this warning. You can look at them. That it was saying that there is no match from, but now we did. There is a from, so the warning is not there. So it looks fine, the DQ to ABC transformation, but to test that it's working fine, we can give a constant values to the or we can define constant values as the UD and UQ. Now it is 1 and 0, so we expect that the converter is producing a UD of 1 and a Q of 0. If we run it, we see that the model runs and it's giving some outputs. To make sure that somehow it is working properly, we can change the amplitude and also angle of the voltage, of this voltage. Now we have changed both amplitude and the angle, so we expect that both active and reactive power are become non-zero. So if we look at we can see that there is a current now flowing in the system, and also the P and Q are not zero. So it's something that matches our expectations. That means this block is working properly, so we can connect the input ports. Before going inside the controller, if you want to open these masks by double clicking, we can remove the parameters or dialog box, since we are not going to define any parameter value for these masks here, so we can remove them and by going to edit mask. Now we also remove this parameter, and now we can open this mask by double clicking. So let's do the same for other two uh, uh, blocks here by removing the parameters and dialogues on these masks. Now we don't need to look under the mask or so. We can simply open them by double clicking. So now let's run the model. Now we face an error. The error says that there is a mismatch in the dimensions. The problem is that we haven't connected anything to UDQ. When we don't connect, it is considered as a one dimension or for example, 0. But it should be actually two-dimensional or a vector, that's UDQ. To test it, we can add this 1 and 0, give it as a vector, and see that the error is not there. So it means that was really the problem. So for now, we have DQ ABC block working. We can build up also the ABC to DQ block. Here we need to obtain IDQ and UDQ. We can use the omega t that we already obtained from the measured voltage, and always make sure that the visibility of these go-tos are local, so they will not be disturbing any other signal in other blocks. Now if we run it and look at in the scopes after we can see there are three actually. Let's change the layout so we have voltage on top and current at the bottom. We can see there are three signals because that is ABC to DQ0 transformation. But we need for our controller to only U and D, UD and UQ, or only DQ components. So we can make another subsystem or whatever that receives this AB receives DQ0 and gives only DQ components of the signal. We can always create a mask and remove the parameters. Then yeah, let's rename the input and output ports. Then we can use it for both voltage and current. Now if we run it, it will run properly, and the UDQ and IDQ are actually now two-dimensional, so they are two signals, not three. Now we have ABC, and we have built up the ABC to DQ and DQ to ABC. Now let's build up the controller. For controller, we need a PI controller. We use PI controller for one for D axis and another for one for Q axis. The P we use PI. So and in the discrete domain, we need to define the control parameters. So let's call them KP current control of. So we know that it belongs to current controller, and also same for the integrator. We can make a duplicate of that, so the settings will be copied also. Now we need to give the error signal, which is the difference between measured and the reference value. We need to give this error signal to the PI controllers. So here we have ID and IQ. Let's separate them, and then we can use it separately for D, which is on top, and also Q that is on the bottom. It's important to notice that the order is important here, because it is UDQ, so D should be on top. When we combine these signals, the top one will be the first. We can give some constant values as a reference current here, and run the model. As is expected, we need to define the variables for the control parameters in the script, so the Simulink will recognize them. Yeah, let's add two comment or percentage sign, so it makes a new section in the script, which helps for visualization purposes. So let's define KP of and KI of the current controller, which is 12.5. Yes, 12.5. And yeah, this is current controller. And save it. We don't need to run the script because we made that callback function, which will run the script before performing the simulation. It is running. Yes, if we look at the scopes, we can see, yeah, the current is 1 because we gave one ID and IQ 0. Here we can see that P is actually 1 and Q is 0 because D is related to active power and Q to reactive power. We can test also the performance of the current controller by giving the step signals to them. So let's define a step one for ID and another for IQ. Let's change the stepping time for Q to 1.5. Yes. And also we can visualize the measured current. Now we know that there is a step at t equal to 1 second for D and for ID, and at 1.5 second for IQ. If we look at the measured current, we can see that the currents are following the uh, set points, which looks fine. Also, we can see the impact of this current on the P and Q. So again, we can see that P is really related to ID and Q is related to IQ. Here at the moment we are using we measure the signal and we use it in a feedback loop. It's always good to add a delay to avoid the because sometimes it gives the algebraic loop error, and also it can slow down the simulation. Now after adding this, we can see that really the simulation runs faster. Now by doing so, we are sure that our current controller is working properly. So we can collect the correspondent blocks and make a subsystem and call it a current controller. Yeah, we can name the input and output signals. This is measured signal or measured currents, and the one on top should be reference values of the current. Also, let's make this go-to blocks for also reference currents, so it looks better. Yeah, let's copy them and rename them to reference. Now we can get a from block from these signals and give them to the summation block. Yeah, it looks fine. Again, we can always test the model to make sure that we haven't changed anything that gives us error. So it looks that the model is working still, and yeah, the power and yeah, active and reactive power are behaving as we expected, and also the currents. We can see ID is going to 1 and IQ is 0, as it is defined in the set point values 1, 0. Let's create a mask for this current controller also. So we don't need any parameter or dialog. We can save it. Yes. Also, let's rename this output signals. That will be the voltage, the reference voltage to the converter. The naming it doesn't matter. It's just for understanding the signals. For example, we can call it UDQ conv, so we know it's going to converter. But it really doesn't matter, or it doesn't change the performance of the model. Now let's make a copy of this controller. I'm making a copy because the these two controllers are very similar to each other. So we just need to change the names and also the settings of these PI controllers. So we can do it as P reference value, and this one should be Q reference. This one P measured and Q measured. Yes. Now let's replace these blocks with the PQ ones. Yeah. We need to define the new variables for the controllers because it's a power control PQ controller, so we can uh, do that and also define these new variables in the script. Let's call this one grid side controller because this is grid side of the wind turbine. So we had the current controller, now we add the power controller as well. It should be KP power control and KI power control. The values should be 0.2 and 30. We don't focus on the tuning of the controllers. Just use these values and they should work fine. In the future, probably we will focus more on these tuning aspects or the dynamic behavior of the controllers. Now let's run the model. and look into the scopes. Now we can see that it's somehow unstable, doesn't behave as was expected. The beauty of running the simulation at each step is that we know uh, which blocks introduce these instabilities. So now we added these PI controllers, so we can understand that that's coming from here. As it's not always straightforward, but now to save time, I just can say that it's because of the limitation on the uh, this controller of PQ, because it gives the reference value of the currents. Now by adding limitation to these PI controllers, we are avoiding any um, large giving any large signals to the current. That fixed the problem as we saw here. Here we can see the point that I mentioned about the icon transparency. Now, if we change it to icon with ports, we can see that the port names are visible on the block, even if there is a wind turbine picture on the this mask. So we know that that is PQ ref. Let's connect. Let's give some, yeah, 2 steps for active and reactive power set points. Yeah, let's change the set points yes to 1.5 and run it. It should be a stable now because we added that limitation. We can see that P is actually following the set points, but Q is not. So we need to go to the Q controller and see what is the problem. The problem here is due to the power sign convention actually, and the equation for that we use for calculation of reactive power. Let's make it simple and just add a -1 to multiply Q ref and Q measured by -1. So if by doing so, uh, here we don't go deep inside the dynamic performance of the controllers. So that is why I don't spend time on explaining exactly why we need this -1. But if we add it, we can see that now reactive power is also following the set points at 1.5. It's going to 0.5 per unit. And also we can see the impact of these powers on the current. Yeah, it looks fine. And also the currents. These are the measured IDEQ currents. The difference here is that these reference values are not the reference that we give. They are the reference defined by PQ controller actually. So let's plot also the reference values. Now we can see that the current controller or the measured current are following the reference signals. So it means our current controller perform very fine. Also, we are not using this UDQ measurement in this module. It will be used to improve the performance of controller, but here let's just terminate it. And also, as always, we can do formatting on our blocks. So based on your preferences. As I mentioned before, this is not changing. This formatting will not change the performance of the model. It's just for visualization. Yeah, so do it as you like. Yeah, it looks with it for, yeah, this ones. You can change for example, the background color of PLR or this ABC to DQ transformations. That's easy to do. Yes, I mean, if you like, it looks good. This one orange, yeah. This one's dark green and yellow. Yeah, this formatting helps to find the components. For example, if we make the scopes green, it's easier to find them and whenever we want to open them. Now let's run it. It shouldn't have changed anything as we did only formatting. Yes, it looks working, just to double check. And we can do final formatting on the main page of the model. Now let's change also this solver because now it is auto, but we know that our model is fixed time discrete, so we can set the solver to that. That helps, and we somehow will speed up the simulation. As yeah, and finally, in the final step, we can add a parameter and dialog box to the wind turbine mask just to test. So let's write here wind turbine. This is wind turbine model. And for the description, we can probably copy this text here. So let's make it today, 13 April. And yeah, let's copy it here and save it. Now, if we double click on the wind turbine model, we can see that, yeah, this description and the title are there. Also, we can add parameters to receive the parameters here. Let's, for example, start with nominal values. Yeah, and the name is nominal value. This name is the name that will be recognized inside the model. So, for example, if we have power, let's say, and then name it as SNOM wind turbine, and also open we can see that there is this uh, box that we can insert the values. We inserted 10. Now if we run it, the model, we can see that our current is scaled a lot, and the problem is that we used similar name for the on the editor mask as the one on the script, which was SNOM wind turbine. Now we could see it was 10, which is the value that we inserted. Let's change it to SNOM wind turbine 0. So now it should be more clear to you. Now we can see SNOM wind turbine is 8 megawatt actually, but SNOM wind turbine 0 is 10. But not to change the variable names inside wind turbine model. We will use same variable names here, but make sure that you are aware of this fact that it will overwrite if there is a SNOM wind turbine outside the model. Let's add these units. Yes, another is frequency for nominal values, hertz. This adding units helps the user to understand in which unit they need to insert these parameter values. And we are using same names as you see, FNOM wind turbine, VNOM wind turbine. Now let's make it SNOM wind turbine as it was. And yes, and also in the script we called it VNOM wind turbine. Yes. Yeah, it's better to make this volt ampere the power unit probably, and also do some change in the layouts. So now the text box should be on the same line for nominal values as you see, so it looks better. Now we can add more group box here for other parameters that we want. For example, which components do we have in the wind turbine model? We have transformer, for example. Yeah, let's name it transformer. Now we can add to edit for receiving the resistance and inductance of the transformer from user. For the naming of these variables, let's copy it from the transformer just to make sure they are matching. But be aware that this will be rewritten. So this will be the value that is inserted on the dialog box of wind turbine. It doesn't matter if you define it on the script. So just keep that in mind. And here also we can this now this value is the one in the workspace of the MATLAB, because it's not inside the model, inside the wind turbine model. Yeah, we can do layout. So location, current line, current row. And also probably let's add another nominal voltage because there is a transformer in the model. So we receive both high and low voltage for this transformer. Let's use the same as vnom grid. Probably it was better to use the vnom low and vnom high here, but not to change the model. Let's use the same variable names that we used in the script. Okay, it looks fine. Now we can add more group box also for other components or for other things. So one thing is also this filter, RL filter that we have. We can add some edit box to receive the values for resistance and reactance of. Yes, let's copy them from here. Yes, resistance. And make sure that you write these units there, so we know that filter we are receiving as ohm and Henry, but for transformer it's per unit, because normally we could receive for filter also in per unit and change it inside the model to physical values, but let's just make it simple. Also we can add another group box for DC link to receive also the DC voltage. And similarly for the controllers. So we have this grid side PQ and current controller. We can add a subgroup box for each controller. So one for PQ controller, and receive the KP and KI for this controller. Yeah, let's add edit to edit, and one for KP, one for KI, and let's use same name that we used here. Yeah, let's copy it, KP, and similarly for KI. Doing the layout. Now we can add another sub group box for current controller as well. One for KP, one for KI. And the name was KP current controller, if I'm right. Yes, KI current control. And doing the layout, we can save it. Now it looks fine. So we have all these nominal value, transformers, filter, DC link, and the controllers. Maybe it's better to yeah, first let's insert the values for these variables, filter, and later we can change this group box to collapsible panels, so they will not be opened whenever we open this dialog box. But yeah, let's finish the variable name. Now we can edit the mask. Going to mask editor. Here, if we choose group box, we have the option of collapsible panel. So we can change them to collapsible panel. Yes, this one. Yeah, or maybe it's better to have this description of the model as group, so it always will be shown. But the rest, they are collapsible now. Yes, it looks better. Now we can make the final check also always. Yeah, there is an error that nominal voltage of winding. Winding is related to transformer, so it should be a voltage related to transformer. Here we can see it's 0. So you can see, even so it is defined in the script, but the value on the dialog box was 0, so it was used inside the model. Now if we use the correct variable there also, we can see the model runs properly, and now the scale of current is also fine, and we can see PQ as well. It looks fine. They are following the reference values, which is 1 for P and 0.5 for Q, and that's it. Yeah, this is the model for module 1. Thank you.